Okay, welcome back. I want to do this example here in detail before I go to variable force. And so it says a 70 kilogram skier gliding at 2 meters per second when he starts down a very slippery 50-meter long 10-degree slope. So very slippery meaning ignore friction. What is his speed at the bottom? Should be capital letter. What's his speed at the bottom? So I will do it two ways. One of them, Newton's laws, the first way, and then I will use the work energy principle to do it. Solution. Using Newton's laws, we know that, let's draw a picture here. So this is our x-axis this way. This is the x-axis. And the y-axis, so the x-axis is this way, parallel to the slope, and the y-axis is perpendicular to it. So here is the skier, and the forces acting on the skier are the force of gravity, and then there is the normal force this way. And we know that the normal force is the force of gravity times the cosine of the angle, but what causes the acceleration is this way, is the component of the gravity. It's the mg sine theta along the x direction. That's the force of gravity. This component of gravity this way is mg cosine theta, and that's the normal force that way. So if you like, you can write that the force of gravity will have two components. One of them is along the x direction, which we define along the slope. It's mg sine theta, and it's along the x direction, so it's I hat. And then one of them is the y-axis positive is that way, so this is negative, so minus mg cosine theta j hat. The normal force will be, it's along the y direction, so it's along the positive y direction, so j hat, and it's equal to the y component of the force of gravity, because there is no motion this way, so it's mg, it is mg cosine of theta. So the net force, therefore, the net force, F net, the net force, which is the force of gravity plus the normal force, and that will give me what? You add these two cancel there, zero, they add up to zero. So I'll have mg sine theta I hat, right? So the net force is simply along the x direction, so the acceleration will be along the x direction. So using Newton's laws, I know that the net force equal to the mass times the acceleration. So the acceleration will just be the net force divided by the mass. And so it's the net force divided by the mass. So the net force is mg sine theta I hat divided by the mass, which is m. And you divide those, and you get the acceleration, which you already knew. It's g sine theta. And if you like, it's along the x direction. The magnitude of acceleration is just g sine theta. So what would the speed be down the slope? Well, it's motion at constant force, so constant acceleration. And so the speed would be, you would have v2 squared minus v1 squared is equal to 2 times the acceleration times x final minus x initial. X final is the person ends up 50 meters down here. Initial position is 0, so just 50, or 50 if you like, minus 0. And 50 minus 0. And so you get v2 squared what's v2 squared? I'm sorry. Yeah, you get v2 squared minus v1 squared. v1 is, what's his? Yeah, it was 2. So 2 squared equals 2. 2 times the acceleration, but the acceleration is g sine theta. So 9.8 sine theta, sine of 10 degrees. Okay, sine 10 degrees. And times 50, right? 2a, 2 times the acceleration times the 50. And so you get the speed. Let's calculate the speed. So that's using forces. So we'll have 2 times 9.8 times the sine of 10 degrees times 50 plus 4. And then take the square root of that. You get 13.2. So that V will equal to 13.2 meters per second. That's V2. So the speed down here would be 13.2, and the direction is in the x direction. Let me make sure I got it right before I continue. Yeah, 13.2. Now, I want to do the same thing but using work. So first of all, and I'm going to calculate work in two different ways. So first, I can calculate the work done will be the force times the displacement, right? That's the force times displacement. The force is the net force, and it is mg sine theta, and it's in the I hat direction. So it's like this, mg sine theta, it is in the I hat direction, dot the displacement is displaced from 0 to this way, so the displacement is 50 meters in the I hat direction, in the x direction. So 50 in the x direction. That's my definition of work. And so now I will have this. This is a constant, this is a constant, this is a constant. So mg sine theta, and then times the 50. And then I have the dot product of this I hat dot with I hat, right? I have the dot product of two vectors. These are the vectors, the I hat and the I hat. Now, what is the dot product of a vector with itself? Well, it's here. The dot product of a vector with itself is the magnitude squared of that vector. Is the magnitude of the vector squared. Remember what I hat was. It's a unit vector. It's a vector of length 1 in the x direction. So what's the magnitude of I hat? Well, it's 1. So it's 1 squared, that's 1. So this part here is just 1. And so you get simply, so this is 1, that goes away, and you get mg sine theta times 50. So the mass is, let's do that. Yeah, so it's 70 for the mass. G is 9.8 times the sine of 10 degrees, and then times the 50. All right? And so that is the work done. So let's see what we get, how much work we got done. So we get 70 times 9.8 times the sine of 10 degrees times 50, and you get this large number, 7,658. 7,658 joules of work. Now I know that using the work energy relationship, I know that the work is equal to the change in kinetic energy. So the kinetic energy at the end minus the kinetic energy at the beginning will equal to the work done. The kinetic energy at the end is 1/2 the mass times the speed at the end squared, minus the kinetic energy at the beginning is 1/2 m times the speed at the beginning squared, v1 squared, equals to the work done, 7658. And so I get here 1/2. The mass of the person is 70, and then v2 squared minus 1/2. The mass of the person is 70. v1 squared, the person was moving at 2 meters per second squared, so 2 squared. So that's this part. equals to 7658. And I will let you solve for V2 on your own. Well, guess what you will get? You will get 13.2. And in fact, I'm going to do that. Let's solve just to double check. So I have 7658. Okay. Multiplied by 2. Divided by 70. 4. Did I make a mistake somewhere? Let me see. Just check my work here. Okay, I'm double checking my work. I think I made a mistake here actually. This should not be 7658, it should be 5956. 5956. That's why it seemed like the number I got was larger. 5956. And now V2 will give me the 13.2 I thought I would get. 13.2 meters per second. All right. And now I'm going to do the work using a different method. This is using Newton's laws. This is using components directly. And now I'm going to do it looking at the picture and using the angles. Now, the work done by the normal force will be the normal force times the distance moved times the cosine of the angle that the normal force makes with displacement. Displacement is this way, the normal force is that way, so they make a 90-degree angle. So this is 90 degrees, and so that ends up being 0. Normal force does not do any work. The work done by gravity will be the force of gravity times the distance moved times the cosine that gravity makes with that. What angle does it make? Well, gravity is this way, so what's this angle? Well, this is 90. I know this is 10, so this is 80 degrees. So gravity makes an 80-degree angle. Cosine of 80 degrees. And cosine of 80 is the sine of 8. I'm sorry, the cosine of 80 is the sine of 10. Is the sine of 10 degrees. So anyways, let's see. The force of gravity is mg. So this is mg. So it's the mass, which is 70, times gravity, 9.8. Distance moved is 50. Times the cosine of 80. If you do that, you will get cosine of 80 again is the sine of 10. So you get 70 times 9.8 times 50 times the cosine of 80. And you get 59, 56. 56. Oh, I failed to correct this one. This should be what? 59, 56. 56. I corrected it here and here, but I forgot to do it here. And so that's the work done by gravity. And so the total work, really the work done by the normal force plus the work done by gravity. And so that's 0 plus 59, 56 is 59, 56. And so since you have the total work, it's equal to the change in kinetic energy. And so you will use exactly this step to find the speed, and you will find it to be 13.2. In practice, when you're solving physics problems like this, usually you will just use this part here where you use the cosines of the angles because they're clear. You're rarely given a force where you have the components. Somebody gives you the components and say, calculate the dot product. I mean, it can happen in textbook problems, but usually if you want the dot product, you will have to find the components yourself, like we did here. Okay? So now, let us go to the more general one. I will do the work in one dimension with a variable force, and then we will do the work in 2 or higher dimensions, and then with also a general force, and then we will see what we get. So up to this point, we considered the forces to be constant, and therefore the acceleration is constant, and then we use that kinematics in one dimension to find the change in kinetic energy. But is work equal to the change in kinetic energy in general? By our definition of kinetic energy, that kinetic energy is 1/2 mv squared. And the answer turns out to be yes. And so here is how we're going to do that. We're going to use our definition of work. And so we will say the force, first of all, will not be constant, but we're still moving in one dimension, right? The force is along the x direction. And when I write F now, is the force along the x direction. Okay? It's just a component of the net force that is along the x direction. So I know that the net force on an object will equal to the mass times the acceleration of that object. At every instant, whatever the force is causing such an acceleration at that particular instant. Even if the force is changing. If it's changing, the acceleration will also be changing. But the acceleration is the time derivative of velocity. It's the mass. Let me go here. It would be the mass times dv dt. So your object is here and you're here. So as you move along the x-axis, the velocity is changing. So the velocity is a function of where you are also along the x-axis. So I'm going to use the chain rule and say that this dv dt will be dv dx, because x, the velocity is a function of where you are along the x, and then dx dt. You may have seen this before, right? If you can think of it as like, if you cancel these, it goes back to dv dt. And that's in fact how you derive the chain rule. So now, all right, so let's continue. So I have F would be dx dt is v, so I'm going to write that in front here. So I have m v dv dx, dv dx, dv dx. And so instead of saying the work done was the force times distance as earlier, but now the force at every step of the way is changing. So what is the force? So for example, as a function of x, so here is x, here is f, here is f. F could be changing with x. It could be some function of x. So what should I do to find the work done? Well, I will divide the x-axis into little intervals of dx here, a little delta x. If you like, you can call it delta x. And say that the force within this delta x will be constant, So the amount of work I do within an interval delta x is an amount of work called delta w or dw, and it is equal to the force times dx. Whatever the force is at this instant times dx. So let me write it. So dw will be f times dx. But f dx is mv dv dx dx, and dv dx dx, let me just take it slow. So you get f times dx. I'm sorry. F itself is mv, and then dv dx dx. But what is dv dx dx? That's dv. That's how you define the differential dy. dy is dy dx times dx. And so this simply becomes dv. And so we get dw, therefore, a tiny amount of work is m v dv, right? mv dv. That's a tiny amount of work. You can view it, dw is this, and dw is that. So in terms of velocity, I could integrate this and see what I get for the total work. So the work done, the total amount of work, would be the integral of mv dv. And let's say the velocity here is v1, and at the end of my push of applying of the work, it's V2, so it's from V1 to V2. And so this is a variable force now. I'm not assuming it's constant. So what's the integral of this? Well, V dV, the integral of V will be just 1/2 of V squared. So this becomes 1/2, and I still have the mass here, 1/2 mv squared from V1 to V2. And this becomes, you substitute the V at the upper limit and then minus 1/2 mv squared, 1/2 m. So it becomes 1/2 mv1 squared, 1/2 mv2 squared minus 1/2 mv1 squared. So 1/2 mv1 squared, v2 squared, I did one thing and I said a different thing. So 1/2 mv1 squared. All right, so that is that. And this is the change in kinetic energy. So we can box this. So let me just box it. W is equal to the change in kinetic energy. The work done will equal to the kinetic energy 2 minus kinetic energy 1, or we can call it just the change in kinetic energy. This is called the work energy principle, or theorem, sometimes it's called. Okay? It says the work done on an object, you can have several forces, or as many forces as you want. The net work done by those forces is equal to the change in kinetic energy of that object. Okay, and that's it. All right. And I would like to now get the work done using FDX, and see what happens. Okay. And so before I proceed, let me write this one here. The work done, really, this is the starting point. It's W is the integral of F dx. That's what we did. We converted it into something with speed or velocity, and it's from x1 to x2. So, all right. So let's see, how do we integrate this? Well, we need to know the force explicitly, what it is, and also can everything be integrated? The answer is it has to be a single valued function. For example, like this one, it's fine. So let's see what we get. What is the integral of this? Well, we know from the fundamental theorem of calculus part 2, this will equal to g at x2 minus g at x1. You may remember, let me write down the fundamental theorem of calculus part 2. You may remember it this way. The integral of little f of x from, I think they would say x1 to x2, or from a to b, I forget how they write it in calc books at the moment. It will equal to f of b, capital FB minus capital FA. That's how you would see it. Where little f is equal to df is equal to df dx is equal to df dx. So just capital F is any antiderivative of f. Is any antiderivative of f. Okay. And so here, capital G is any antiderivative of f. But aesthetically speaking, this will not look good. So let's see what this is saying. You got the work done is equal to this as a function of x, and this one in terms of the change in kinetic energy, it's equal to that. So let me just write these two. The work is this, and the work is this. So let me write them down. So I get K2 minus K1 will equal to G at x2 minus G at x1. Notice if I try to collect the 2's together on one side, I would get K2 minus G2 will equal to, if you move this one to the other side, you get K1 plus K1 minus G1. You get K2 minus G2 equals to K1 minus G1. We don't like minus signs, and so in physics, what we will say, let a function, so here, G is equal to F is dg dx, right? It's just an antiderivative of that. And let U equal to minus G, all right? So that F will equal to minus dg dx. So minus du dx, minus du dx. I made so many mistakes today. So this is the fundamental theorem of calculus, part 2, assuming we can integrate this. And so f is the derivative of g, but let u, we define new function equal to the negative of g such that f will be minus du dx. So in terms of that u function, will be k2 minus k1, instead of gx2, it will be negative u at x2, because u is negative g, and this one would be minus minus, it would be plus u at x1. And now you will see what I'm going to get to. You get to something nice. Let's move this to this side. You will get k2 plus u2, let me call it u2, instead of u at x2, it would be u2. And then the k, move it to the other side, the k1 will be k1 plus u1, u of x1, I'm calling it u1. And this is called the law of conservation of, in this case, mechanical energy. The mechanical energy of object will equal to k plus u2, k plus u. Mechanical energy, U, is the mechanical energy. More about that on the next chapter. Mechanical energy of an object. It's equal to the kinetic energy plus something else, plus this u. And this u function, we will call it the potential energy. So by definition, the force is equal to negative the derivative of the potential energy. Negative the derivative of the potential energy. Okay? All right. So now, let me see how much time I'm into. Yeah, I will come back in the next video and discuss this one a little bit more.